Volcanology has, for most of the last century, sorted the world's volcanoes into three boxes: the volcanoes that sit on rifts, the volcanoes that sit on hotspots, the volcanoes that sit on subducting slabs. Almost every volcano on Earth fits cleanly into one of them. Almost. Because there is Mount Etna, on the eastern coast of Sicily, with 1 million people living in its shadow, with a lava chemistry that does not match its tectonic position, with a behaviour pattern that has resisted every attempt to force it into the standard categories. New research argues that Etna may belong to a fourth box that nobody had drawn before, a volcano fed by a deep partial melt zone leaking through a broken slab. And while the research is being argued, a small cluster of weak earthquakes has appeared at 28 kilometres depth, on a side of the volcano where small earthquakes do not usually cluster. Quick note before we dive in. If you enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss any of our nightly debriefs. Drop a comment and let me know where you're tuning in from tonight. Let's dive in. Part 1. Something is off underneath Mount Etna. There is a volcano in Sicily that has been erupting for as long as anyone has been writing things down, and there are records of it going back 2,500 years. The Greeks wrote about it, the Romans wrote about it, Pliny the Elder wrote about it, medieval monks in the Abbey of Catania wrote about it, modern volcanologists with seismic networks and satellite radar and gas spectrometers have been writing about it for the last 60 years, and in all of that time, in all of those records, in all of the careful observation that has gone into one of the most studied mountains on Earth, there is one question that has never been answered cleanly. Why does Mount Etna behave the way it does? I want you to sit with that question for a second, because it is going to drive everything else that we talk about tonight. Mount Etna is the largest active volcano in Europe. It is somewhere around 3,357 metres tall, depending on which year you measure it, because eruptions rebuild the cone often enough that the summit elevation moves. It is one of the most active volcanoes on the planet by a number of different measures, whether you count eruptions per century, or paroxysmal events per decade, or simply hours per year, that there is some kind of incandescent activity at the summit. It is so consistent in its restlessness that the town of Catania, which sits at the southern foot of the mountain with a metropolitan population of about 1 million people, has organised itself around the idea that the mountain will erupt, that the airport will close periodically, that ash will sometimes fall on the streets in summer, and that life will go on regardless. Etna is, in the Sicilian idiom, simply there. La montagna, the mountain. And yet, for all that familiarity, for all the centuries of observation, there is one thing about Etna that volcanology has never been able to explain. The volcano does not fit any of the standard categories. Now stay with me on this, because this is the door we are about to walk through. Volcanology has a kind of taxonomy, a list of boxes, a way of saying, this volcano belongs to this category, and that volcano belongs to that one. The categories are useful because they are tied to mechanisms. A volcano in one category is fed by one kind of process. A volcano in another category is fed by a different one, and if you know which box a volcano belongs to, you can make a reasonable guess about what it is likely to do. But Etna does not fit any of the boxes. It has never fit any of the boxes, and a new line of research, work that has been developing over the last several years, and that has been gaining real traction in the literature, is now arguing something that, if it holds up, will rewrite the way we think about this mountain. The argument is that Mount Etna may not be a normal volcano at all. It may be something new, a type of volcanism we have not classified before, fed not by a magma chamber, not by a hotspot, not by a normal subducting slab, but by something stranger than any of those. A deep, partially molten layer of the mantle that is leaking upward, slowly, through folded and partially stuck slab structure beneath the island. A leaking pipe, from deep inside the earth. And this would be just an interesting piece of academic taxonomy, the kind of debate that volcanologists have at conferences over coffee, except for one thing. While the literature is reaching this conclusion, while the modelers and the seismologists are putting together this strange new picture of what is actually feeding Mount Etna from below, the volcano itself is doing something. A small cluster of weak earthquakes was recorded west of the mountain, at depths around 28 kilometres, which is about 17 miles below the surface. A weak thermal signal has appeared in the northeast crater, captured on a recent Sentinel-2 infrared satellite image. The source of the volcanic tremor at the summit has shifted, in the last weeks, toward the northwest. None of these signals on its own would mean very much. On most volcanoes, on most days, none of them would even be reported. But on Etna, the small signals matter, and the reason they matter is that this is not, as the new research is starting to argue, a simple mountain with a simple magma chamber. This is a volcano whose plumbing system can change, and on a volcano whose plumbing system can change, a deep earthquake in a new place, a thermal signal in a crater that has been quiet, a tremor source drifting toward a flank that has been silent. Those signals add up to a question that is worth asking out loud. Is Etna's deep system beginning to reconnect with the summit again? And if it is, which part of the volcano is going to be the part that responds? That is the story tonight. That is what we are going to walk through together. The new picture of what is actually underneath Mount Etna, the small signals that are coming back, the long, slow slide of the volcano's eastern flank into the Ionian Sea, and the question of which part of a system this complicated is changing right now. By the end of the night, you will understand why a few magnitude 2 earthquakes in a place no one has been paying attention to may matter more than they look like they should, and why a volcano that scientists have been studying for 2,500 years can still, in 1926, surprise us. So let us start with the question itself. Why does Etna not fit? Part 2. The 3 boxes and the 1. Etna will not sit in. Volcanology, for most of the last century, has been organising the world's volcanoes into 3 broad groups, 3 boxes, 3 categories tied to 3 mechanisms, and before we can talk about why Etna does not fit any of them, we have to understand what the boxes actually are. The first box is for the volcanoes that sit on top of places where the planet's tectonic plates are pulling apart. The crust thins out, the mantle underneath wells up to fill the gap, the pressure on the rock drops as it rises, and rock that was solid at depth begins to melt, because the melting point of mantle rock is sensitive to pressure. This process is called decompression melting, and it is what feeds the volcanoes of the mid-ocean ridges, where most of the planet's volcanism actually happens, hidden underwater, mostly out of sight. It is also what feeds the volcanoes of Iceland, which is one of the very few places on Earth where a mid-ocean ridge sticks up above sea level. If you have ever seen footage of fissure eruptions in Iceland, of long cracks opening in the ground and lava welling up out of them in lines that stretch for kilometres, you have seen a divergent zone volcano in action. The magma is born of the simple geometry of plates moving apart. The second box is for the volcanoes that sit on top of what we call hotspots. A hotspot is a localised plume of hotter than average mantle material that rises slowly, over hundreds of millions of years, from deep inside the planet. The classical model says these plumes come from near the boundary between the Earth's mantle and its molten outer core, almost 3,000 kilometres down, though the actual depth of origin is still debated. What matters is that the plume is more or less fixed in position relative to the deep interior, while the tectonic plates above it drift across the surface. So a hotspot punches a volcano through whatever piece of crust happens to be sitting on top of it, and as the plate moves, a chain of volcanoes traces out behind it, like a smoke trail across the floor of the ocean. Hawaii is the classical example. The big island, the one you can fly to, is sitting over the active end of the Hawaiian hotspot. The string of older volcanic islands and seamounts stretching northwest from it across the Pacific is a record of where the hotspot used to be, relative to a plate that has been sliding northwest for tens of millions of years. Yellowstone on land is another hotspot. The Galapagos, Reunion, the Canary Islands, all hotspots. The magma is born of a deep, narrow column of upwelling mantle. The third box is for the volcanoes that sit on top of subduction zones. A subduction zone is where one tectonic plate slides underneath another and descends into the mantle. It is the most violent of the standard volcanic settings, because the descending slab carries water with it, mostly bound up inside the minerals of the oceanic crust that is being shoved down, and that water gets released as the slab heats up. The water rises into the wedge of mantle above the slab, and water in hot mantle rock lowers the melting point. So the mantle wedge melts, the magma rises, and a volcano forms in the overriding plate, typically tens to 100 or so kilometres behind the trench, depending on the angle and the speed of the subducting slab. This is the engine that builds the Pacific Ring of Fire, the volcanoes of the Cascades in the American Northwest, the volcanoes of Japan, the volcanoes of the Philippines, of Indonesia, of New Zealand, of the Andes. All of them mostly run on the same basic mechanism, a slab descending, water released, mantle wedge melting, magma rising, mountain growing. This is also, in a much more complicated form, the engine that builds the volcanoes of southern Italy: Vesuvius, the Aeolian Arc, the Campi Flegrei caldera near Naples. The Tyrrhenian Sea has been doing subduction in its own messy regional way for a long time. Magma is born of slab water flushing the overlying mantle. Those are the three boxes: decompression at rifts, plumes at hotspots, slab flux at subduction zones. Almost every volcano on Earth fits cleanly into one of them. Almost. Because there is Etna. Etna is in Sicily, which sits in the eastern Mediterranean, in a region where the African plate is moving slowly northward and pressing into the Eurasian plate. There is subduction happening in the broader region, but the geometry is complicated. The Ionian slab, a section of old oceanic crust that has been sinking beneath Calabria, the toe of the Italian boot for tens of millions of years, descends to the north of Sicily, and volcanoes do exist in that arc. The Aeolian Islands, north of Sicily, Stromboli, Volcano, Lipari, are classical arc volcanoes, sitting in the position the subduction model predicts. Vesuvius and Campi Flegrei, on the Italian mainland to the north, sit in a more complicated piece of the same broader system. These all fit the subduction box more or less. But Etna is south of all of that. Etna sits on the eastern coast of Sicily, on top of the African foreland, the part of the African plate that is being pushed up against Europe. It is in the wrong place to be a normal subduction arc volcano. It is not where the slab water should be feeding the mantle wedge. If you take the standard arc volcano model and you project the geometry onto a map of southern Italy, the line of arc volcanoes points to the Aeolians, not to Etna. Etna is offset. Etna is in a position that the basic geometry says should not have a volcano in it at all, and it is not a hotspot. There is no confirmed mantle plume directly beneath Etna. There is no chain of older volcanoes stretching off across the Mediterranean tracing out a plume track. There is no thermal signature in the deep mantle imaging that looks like a Hawaii-style plume route. Etna is, by every plume diagnostic we know how to apply, not a hotspot volcano, and it is not at a rift. The Mediterranean is full of complicated tectonics, but Etna is not sitting on top of a place where the plates are simply pulling apart and the crust is thinning to let decompression melting happen. The setting is too compressional for that, so Etna does not fit any of the three boxes, and the lava chemistry makes this worse, not better, because Etna's lavas look in some ways more like the lavas of a hotspot volcano than the lavas of an arc volcano, even though there is no hotspot beneath it. The current Etna magma is classified as an alkaline sodic trachybasalt, with elevated concentrations of potassium and sodium relative to what you would expect from a typical subduction setting. Those alkaline signatures are usually associated with the kind of decompression melting that happens at hotspots, or in unusual tectonic situations where mantle is being asked to melt at greater depths and lower percentages than is normal. The chemistry is, in a word, weird. So Etna sits in a tectonic setting that should not produce a volcano, with lava chemistry that does not match what little geometry it does have, and a behaviour pattern, frequent paroxysms, intermittent flank eruptions, persistent degassing, slow eastward flank slide into the sea, that does not look like the textbook arc volcano next door. For decades, the volcanology community has tried to fit Etna into one of the three boxes anyway, with various contortions of the standard models. Etna as a weird arc volcano, Etna as a buried plume, Etna as a piece of opening rift system that does not show up on the surface. None of the proposed fixes has fully worked. None of them has explained the whole package, and that is where the new research comes in. The argument is not you take one of the boxes and you push the lid down harder. The argument is, what if Etna is a fourth box? What if Mount Etna belongs to a category that volcanology, with its three neat groupings, has not yet drawn a line around? What if Etna is not a normal magma chamber with a normal feeder? What if it is, as I said at the start of the night, a leaking pipe from a deep, partially molten layer of the mantle? Which means we now have to talk about what that layer actually is, what we know about it, and why magma from it does not usually escape, except, apparently, here. Part 3. The leaking pipe from the mantle. To understand what the new research is saying about Etna, we have to talk for a moment about something called a low-velocity zone. The name sounds technical. The idea, once you sit with it, is almost embarrassingly simple. When seismologists want to know what the inside of the planet looks like, they have to use indirect methods, because nobody has ever been more than about 12 kilometers down into the crust. The deepest borehole ever drilled, the Kola super-deep borehole in Russia, made it to a little over 12,000 meters before the heat and the rock pressure stopped it. The radius of the Earth is 6,371 kilometers, so in terms of how much of the planet we have ever directly touched, the answer is somewhere around 0.2%. We have scratched the skin. We have never even gotten through the outermost layer. Everything else, everything below 12 kilometers down, we know about indirectly. The main indirect method we have is seismology. When earthquakes happen, they send out waves of energy in two main forms called P waves and S waves. P waves are compressional. They squeeze and release the rock as they travel, and they move through anything: solid, liquid, gas. S waves are shear waves. They shake the rock side to side as they travel, and they only move through solids. By recording when these waves arrive at hundreds of seismic stations around the world, by carefully timing them and comparing what the waves did with what the equations of elastic wave propagation say they should have done, seismologists can build up a picture of the interior of the planet. Where are the boundaries? Where does the crust end and the mantle begin? Where does the mantle end and the outer core begin? Where are the regions of unusual structure? And in the building of that picture, there is one observation that comes up over and over again in places where volcanoes are unusually active. Seismic waves slow down. They are not blocked. They still get through, but they take longer than they should. A wave that should be travelling at, say, 8 kilometers per second in the upper mantle is, in certain regions, travelling at 7 kilometers per second instead, or 6.5, or 6. When a seismic wave slows down like that, it is telling you something about the rock it is moving through. Hot rock slows seismic waves down because heat makes rock softer and more compressible. Damaged rock slows them down because cracks and grain boundaries scatter the energy. But the single biggest effect, the thing that drops the wave speed the most, is the presence of even small amounts of partial melt. Rock that is partially molten, a few percent of the volume is liquid magma, the rest is still solid mineral, is dramatically slower at passing seismic waves than fully solid rock. The little pockets of melt act almost like microscopic shock absorbers, dissipating wave energy and slowing the pulse down. So when seismologists find a region where the waves are slow, they're usually finding a region where some of the rock has begun to melt. And when those regions are extensive, when they form layers, not just pockets, we call them low-velocity zones. A low-velocity zone is, in plain language, a layer of partially molten rock. The melt fraction is small, usually only a few percent. The rock as a whole is still solid enough to support the weight of everything above it. But there is enough liquid magma scattered through the layer on a microscopic scale to noticeably slow down the seismic waves that pass through. And the rock is, in some real sense, primed. It is closer to melting than the rock around it. It is on the edge. Low-velocity zones exist in a number of places in the planet's upper mantle. The one that we are interested in tonight is the one that has been imaged beneath the eastern Mediterranean, at the top of the mantle, beneath the deformed and complicated slab structure that the African plate is making as it pushes north into Europe. There is partial melt down there. There has been for a long time, and in most of the places where it exists, it stays down there. The overlying crust and lithosphere are thick enough and intact enough to seal it in. It can sit, primed, for tens of millions of years without anything coming up. But here is the new picture, the one that this volcano research is now arguing. At Etna, the seal is broken. The slab structure underneath the eastern Mediterranean is not a clean piece of plate sliding smoothly into the mantle. It is folded. It is deformed. In places it appears to be torn. There is published work arguing for what is called a slab tear underneath the western edge of the Ionian slab, a discrete rupture in the descending plate that creates a gap. In other places the slab seems to be partially stuck, not detached, not freely descending, but caught against the overriding plate and folded into compressive configurations. And the geometry of these folds and tears and stuck regions, when you map them out, lines up unsettlingly well with the position of Mount Etna. So the argument is this: the folded, deformed, torn slab structure under the eastern Mediterranean creates weaknesses, networks of fractures, corridors of damaged rock, places where the lithosphere is thinner or more permeable than it normally would be. And those weaknesses provide pathways that connect the deep, partially molten low-velocity zone at the top of the mantle to the surface. Magma, small percentages of melt slowly migrating upward, can use those pathways to escape, to leak. Not in a single great pulse like a hotspot eruption, not in a continuous arc magma factory like a subduction zone, but slowly, unevenly, through a system of conduits that themselves shift over time as the slab keeps deforming. That is the leaking pipe. That is the new picture. Mount Etna, in this model, is not fed by a single confined magma chamber sitting at some specific depth beneath the volcano. It is fed by a deep, partially molten layer that exists across a much wider region of the eastern Mediterranean upper mantle. And what makes Etna a volcano, while most of the rest of that layer stays bottled up, is the specific geometry of the slab tear, the slab fold, the slab edge. Whatever combination of all of those is happening right under Sicily. It is the geometry of the wound in the slab that turns the partial melt at depth into a volcano at the surface. And here is what makes this idea important, beyond the satisfaction of finally having a model that fits. If Etna is a leaking pipe rather than a chamber and a feeder, then the pathway can change. The pathway is not a single dike rising vertically from a single sill. It is a network, a complicated, fracture-controlled, slab geometry-sensitive network. And networks reorganize, cracks open, cracks close, pressure migrates, magma finds a new way up, and on a volcano whose feeder system can reorganize, the volcano's behavior can reorganize too. The chemistry of the lava can change as the pathway changes, the location of the eruptions can change, the frequency can change, the proportion of summit activity to flank activity can change, which is exactly what the geological record at Etna shows. The volcano has been doing all of those things, changing chemistry, changing eruption style, changing vent positions, changing tempo, for as long as we have a record of it. The standard models could never quite explain why. The leaking pipe model not only explains why, it predicts that this is exactly what such a volcano should do. And the central thread of tonight's story comes back into focus right here. Because if Etna's pathway has changed before, and the new framework explains how and why, then the small signals coming back to the volcano right now, the deep earthquakes west of the summit, the thermal anomaly in a quiet crater, the tremor moving northwest, are not random noise. They are the kind of pattern the new framework predicts. The system reorganizing, the pathway shifting, the leak finding new directions, and we are watching it happen in real time on a volcano with 1 million people living in its shadow. Part 4. The lava has been changing, and that means the engine has been changing. If you want evidence that the engine underneath Mount Etna has been changing over time, the easiest place to look is the lava itself, because lava is, in the most literal sense, a piece of the engine that has come up to the surface. You can pick it up, you can run it through a mass spectrometer, you can crush it into powder, melt it down, look at the proportions of every element in it, and read off from that chemistry, where it came from and how it got here. That is the kind of work that has been done on Etna for the last 100 years. Tens of thousands of samples, cores from the volcano's own flanks, lava flows of every age, outcrops that record eruptions from before the Romans were a civilization, and when you assemble all of that into a single record, the picture is unmistakable. The chemistry of Etna's lava has changed over time, not subtly, not by a little bit, by an amount that, in a normal volcano, would not be expected. The oldest Etna lavas, the ones from very early in the volcano's history, and we are talking about a volcanic system that has been active in this location for roughly 500,000 years, give or take, are more tholaitic. That is a technical word that means relatively iron-rich, relatively silica-rich for a basalt, and relatively low in alkali metals. The kind of basalt you find at mid-ocean ridges, the kind of basalt that the planet is made of mostly when you scratch the surface. Over time, Etna's lavas evolved, not in a single jump but gradually. With overlap and back and forth, the chemistry shifted. The silica content modulated, the iron content shifted, and most distinctively the alkali metal content, the concentrations of potassium and sodium in particular, climbed. The lavas became more alkaline, more sodic. The current Etna magma is classified by petrologists as a sodic trachybasalt, with elevated concentrations of potassium oxide and sodium oxide relative to what you would expect from a typical arc volcano, and relative to what Etna itself was erupting hundreds of thousands of years ago. Now, in a normal volcano, you would not expect to see this kind of compositional drift, a volcano that is being fed by a single, well-behaved magma source, with a stable plumbing system that conducts the magma from depth to the surface in a consistent way, should erupt lavas that look basically the same over time. There can be small fluctuations. There can be evolution within a single eruptive cycle, as a magma chamber cools and fractionates. But over hundreds of thousands of years, with a stable feeder system, you do not expect the volcano to march steadily from one basalt type to a different basalt type. That kind of compositional drift implies that something about the source, or the pathway, or both, has changed. There are three main ways a volcano can change its lava chemistry over time. The first way is that the source itself changes. The volcano starts melting a different region of mantle, or starts pulling melt from a different depth. The second way is that the percentage of melting changes. A region of mantle that melts only a small amount produces a different chemistry than the same region of mantle melting more substantially, because different minerals melt at different temperatures, and the proportions in the final magma reflect that. The third way is that the pathway changes. Magma that takes a long, slow route through reactive crust will pick up signatures from the crust as it goes. Magma that rises rapidly through a clean conduit will arrive at the surface looking more like its source. So if the route shifts, if a volcano that used to feed its magma slowly through one corridor begins feeding it more directly through another, the lava that comes out can change composition. The leaking pipe model gives you a clean explanation for all three of those at once. If Etna is fed by a partially molten low-velocity zone at the top of the mantle, then the source itself is broad. It is a layer, not a point, and different parts of the layer have slightly different compositions. As the pathways through the slab fold and the slab tear reorganize over time, the magma can start drawing from different parts of the layer. As the geometry of the conduits changes, the percentage and depth of melting along those conduits also changes, and as the route from the source to the surface evolves, the amount of interaction between rising magma and the crust along the way changes too. So under the new model, the long-term chemistry shift at Etna is not a mystery. It is exactly what such a volcano should do. The volcano started its history with one configuration of the leaking pipe network. The slab kept deforming, the network kept reorganizing, the source region the magma was drawing from drifted, the depth of melting drifted, the route to the surface drifted, and the lava chemistry, which is the most accessible record we have of what is happening inside the volcano, drifted right along with all of it. This is more than a satisfying technical detail. This is the strongest single piece of evidence we have that Etna's feeder system is the kind of system the new research is describing. Because there is a difference, a meaningful one, between a volcanological model that fits the current observations and a model that also explains the long-term geological record. A model that does both is a model that is starting to look right. Now I have to be careful here, because I do not want to oversell this. The petrological literature on Etna is enormous. It is still being argued over, and there are competing interpretations of the lava chemistry record that do not require the leaking pipe model to explain. Some researchers argue that the chemistry shift can be explained by changes in the depth of melting in a more conventional mantle setting, without invoking a low-velocity zone and a permeable slab structure. Others argue that the shift reflects mixing between magmas from different sources that were always present, with the proportions changing over time. The leaking pipe model does not have to be true for the chemistry record to be meaningful. It is one explanation. It is the explanation the new research is pushing. But the key point, the point that matters for tonight, is this. Whatever the exact mechanism, Etna's lavas have been changing. The engine has been changing. The route the magma takes from the deep source to the surface has been reorganizing over geological time. And on a volcano whose engine and pathway have demonstrably changed in the past, the question of whether they are changing right now, whether the current small signals are part of another reorganization, is a question you have to take seriously. You cannot dismiss the deep earthquakes west of the summit by saying, well, Etna has always done this kind of thing, because Etna has demonstrably not always done the same kind of thing. The lava chemistry says so, the geological record says so, the mountain itself, in the language of the rock it has been throwing up for 500,000 years, says so. The pathway changes. And when the pathway changes, the volcano's behavior changes. So when we look at the signals coming in right now, we are not looking at noise on a stable system. We are looking at potentially the system continuing to do what it has always done, reorganizing, except that this time we are here to watch. Part 5. The strange tectonic setting of Sicily. To understand why the slab structure underneath Mount Etna is the way it is, folded, partially stuck, possibly torn, we have to back up and look at the bigger picture of what tectonically is happening in the central Mediterranean. Because the slab geometry underneath Sicily is not normal. It is the consequence of a long, slow tectonic argument that the African plate and the Eurasian plate have been having with each other for tens of millions of years, and the rocks under Sicily are still trying to figure out who won. Here is the broad picture. The African plate has been moving north slowly at a rate of a few centimetres per year for an extremely long time. The Eurasian plate, on the other side of the Mediterranean, has been sitting there receiving that northward push. In between, in geological terms, was an old ocean called the Tethys Ocean, which was the sea that separated the southern supercontinent of Gondwana from the northern supercontinent of Laurasia, back when the continents were arranged very differently from how they are today. The Tethys is mostly gone now. It has been eaten by subduction. The Mediterranean is what is left of it, and it is shrinking slowly as Africa keeps pushing north into Europe. Now, in a clean subduction system, the descending plate goes down at a single consistent angle. The overriding plate sits above it, and a clean volcanic arc forms behind the trench. The central Mediterranean is not like that. The geometry is broken up. The slab descending under Calabria, the toe of the Italian boot, the part of Italy that sticks south into the Mediterranean, is a piece of old oceanic crust that has been sinking for tens of millions of years, but it does not have a clean modern subduction trench feeding it. It is, in a sense, an orphaned slab. The active subduction has slowed dramatically or stopped. The slab is still down there, still sinking under its own weight, but it is no longer being fed at the surface by an active trench. And because of the complicated geometry of how the African plate is pushing north, the African plate is not a single rigid block. It has its own internal structure, and the part of it that is colliding with Italy includes the Adriatic microplate and other smaller blocks. The slab under Calabria is being deformed laterally as it descends. The eastern part of the slab is being pulled one way, the western part is being pulled another, and at the western edge of the slab, right where Sicily is, there is published research arguing for what is called a slab tear, a discrete rupture in the descending plate, a place where the slab has, over geological time, actually broken open and torn. If there is a slab tear at the western edge of the Ionian slab, and this is the central proposition of the research, which is well supported in some studies and still debated in others, then it changes everything about what can happen in the mantle underneath. Because a slab tear creates a window, a gap, a region where the descending lithosphere is no longer in the way of mantle flow. Hot mantle material from the asthenosphere can rise into that window. It can come up close to the base of the overriding plate, much closer than it would in a normal subduction setting. And when hot asthenospheric mantle gets close to the base of the lithosphere, it can decompress slightly, melt slightly, and feed the kind of partial melt zone that we have been talking about, the low velocity zone, so the slab tear creates the condition for the deep partial melt. The deformed structure around the tear, the fractured, partially stuck, folded geometry of the lithosphere in the region around the rupture, creates the pathways for some of that melt to leak upward, and right at the spot where the slab tear is most active, where the geometry of the deformation is most permissive, is where Mount Etna sits. That is the argument. The volcano is on top of the wound. This is also, by the way, why Etna's chemistry looks a little like a hotspot's chemistry, even though there is no actual mantle plume. The mechanism of partial melt rising from an asthenospheric source through a permeable lithospheric structure can produce alkaline lava signatures that resemble what you get from a plume system, even though the actual source is much shallower and much broader. The chemistry is mimicking the deep plume look, but it is not produced by a deep plume. It is produced by a shallower partial melt zone that is being allowed to leak. There is also, in some of the geophysical work on the eastern Mediterranean, the idea that the slab tear may be active in the present, not just something that was completed in the past. The deformation that produced the tear could still be progressing, with the tear propagating along its boundary at geological rates. If that is happening, and the evidence is suggestive but not yet conclusive, then the pathway geometry that feeds Etna is itself in a state of slow, ongoing change. The slab is not just torn, the slab is tearing. The cracks are not just present. The cracks are migrating slowly over the timescales that volcanoes care about. That would explain, in a deeper way, why the volcano's behavior reorganizes the way it does. It would explain why the pathway is not simply a fixed feature of a static geological setting, but a feature of an active geological process that the volcano is, in some sense, riding along with as the deeper system continues to evolve. This is the kind of idea that does not get settled in a single paper or a single decade. The work to confirm or refute an actively propagating slab tear involves very fine-grained seismic tomography, careful geodetic measurements of regional deformation over long periods, and modelling work that has to reconcile a range of observations with the constraints of plate motion calculations. The work is ongoing. The results will keep coming in over the next several years, but the framework, the idea that Etna is sitting on top of a slab system that is itself still in motion, is the framework that the new research is pointing toward, and it gives the rest of the picture the kind of internal coherence that a good geological model needs. The same regional tectonic setting also explains why the volcanoes north of Sicily, the Aeolian Islands, Vesuvius, Campi Flegrei, the ones we have talked about before, have such different characters. They sit in different parts of the deformed slab system. Stromboli, for example, is much more of a classical arc volcano, sitting closer to where the descending slab is releasing water into the mantle wedge in the conventional way. Vesuvius and Campi Flegrei sit in another piece of the broader system, with its own peculiar history that produced the deep, alkali-rich, gas-saturated magmas that have made those two volcanoes some of the most dangerous in Europe. Etna, in this picture, is the southernmost member of a family of central Mediterranean volcanoes, each of which is sitting on a different part of a single regional tectonic puzzle, and each of which has slightly different magmatic plumbing as a result. They are siblings, in a sense, but they are not twins, and there is one more piece of the tectonic puzzle that matters for what comes later in our story, which is the position of the eastern flank of the volcano itself. Etna is built on a basement that slopes eastward toward the Ionian Sea. The volcano is, in a real sense, perched on the edge of the continental shelf, with its eastern foot already extending offshore into deeper water. That sloping basement, combined with the active deformation of the region, the active stress field, the ongoing tectonic motion, is what makes the eastern flank of the volcano unstable in the way that it is. The mountain is leaning slightly into the sea, because the rock it is built on is itself leaning that way. The central thread comes back into focus here. The unusual tectonic setting underneath Sicily, the slab tear, the folded lithosphere, the orphan descending plate, the asthenospheric window allowing partial melt to develop close to the base of the crust, is the geometry that makes the leaking pipe model work. Without the slab tear and the deformed structure around it, there would be no pathways for the low-velocity zone melt to reach the surface, and Etna as a volcano would not exist. With it, Etna becomes possible, and it becomes possible in the specific way that the new research is describing, as a leaking system with mobile pathways that can reorganize over time. The tectonics of the region is the precondition for the engine, and the engine, as we have already seen, is the precondition for everything else this volcano does, including, as we are about to see, the small signals that are returning right now. Part 6. The Deep Earthquakes. West of the volcano. I want to walk you through what has actually been observed in the last few weeks at Mount Etna, because this is where the abstract picture we have been building, the leaking pipe, the slab tear, the reorganizing pathway, starts to connect to specific things that have actually happened on the ground in 1926. 3 signals. We're going to take them one at a time, and we're going to talk about why each one matters. The first signal, and the one I want to spend the most time on, is a cluster of small earthquakes that were recorded west of the volcano, at depths around 28 kilometers, which is about 17 miles below the surface. These were small events, magnitude 2 roughly. Not the kind of earthquakes that anyone would have felt. Not the kind of earthquakes that would have made the news in Catania, much less internationally. If they had happened in a different setting, on a different volcano, in a different tectonic context, they would have been logged into the catalogue, filed away, and forgotten by the next day. They are exactly the kind of small background seismic activity that, taken in isolation, does not mean anything in particular. But 2 things about these earthquakes are worth paying attention to: the location and the depth. The location, first. These events are west of the volcano, not east, on the side where the flank is sliding into the sea and where you would expect any deformation-related seismic activity to show up in the conventional models. Not under the summit, where the standard arc volcano picture would have your magma chamber sitting, and where you would expect to see swarms of small earthquakes related to magma movement. West, on a side of the volcano where the seismic activity is, historically, less frequent and less well characterized. A cluster of small events showing up in a place where you're not used to seeing them is a small departure from the baseline. It is the kind of thing that, on a stable system, you might dismiss as random noise. On a system whose pathway can reorganize, it is the kind of thing you start to write down. The depth is the more important detail. 28 kilometers, 17 miles. That depth is meaningful at Etna because it sits in a specific zone of the volcano's plumbing system. The shallow magmatic system at Etna, the pipes and chambers that feed the summit eruptions and the routine paroxysms, sits in the upper few kilometers of the crust. Conventional magmatic earthquakes, the swarms that announce the movement of magma toward the summit before an eruption, typically happen at depths from a couple of kilometers down to maybe 10 or 15 kilometers. Earthquakes at 28 kilometers are well below that shallow system. They are down in the deep plumbing zone, the part of the system that the new research is now arguing is fed by the low velocity zone and the slab structure rather than by anything resembling a simple magma chamber. They are at the depth where the leaking pipe model says the action should be happening, if the pipe is doing something. Now, small earthquakes at 28 kilometers depth at Mount Etna can be caused by several different things. One possibility, the most innocuous one, is that they are reflecting stress transfer in the deep system without any actual magma movement. The rock at that depth is constantly under stress from the regional tectonics. Small earthquakes are the rock's way of accommodating that stress. They do not necessarily imply anything magmatic. A second possibility, more interesting, is that they reflect movement of magma at depth, small parcels of melt migrating through fractures, exerting pressure on the surrounding rock, creating small failures as they go. This is what magmatic earthquake swarms look like in many other volcanic systems. A third possibility, the one that is most relevant to the new framework, is that they reflect reorganization of the deep pathway itself. Cracks opening or closing in the conduit network, pressure migrating from one part of the system to another, the leak finding new directions. We do not, from a small cluster of magnitude 2 earthquakes, get to know which of those three possibilities is the right one. The Italian National Institute of Geophysics and Volcanology, which monitors Etna out of its Catania observatory, has the data. They are looking at the focal mechanisms, the source spectra, the precise locations, the relationships between the events. They will eventually publish a clearer characterization. But what they have said, in the way that careful monitoring agencies say things, is that the events are worth paying attention to. They are not raising the alert level. They are not telling people to evacuate. They are doing what monitoring agencies do, which is logging the data, watching for more events, and asking themselves whether this small cluster is the leading edge of something or just a one-off. What we, as outside observers, get to do is ask the larger question. Why does this kind of event in this kind of place at this kind of depth fit the new picture of what Etna is? It fits because the leaking pipe model says the deep system has pathways. Pathways that can shift. Pathways that can reorganize. And when pathways reorganize, the rock around them experiences changes in stress. Small ones, in many places. The kind of changes that produce magnitude 2 earthquakes at 28 kilometers depth. The pattern of small, deep events west of the volcano is not the kind of pattern that a stable magma chamber model would predict. It is the kind of pattern that a network of mobile conduits, slowly redirecting under the influence of the deforming slab below and the volcano above, would predict. The events, in this reading, are the signature of the network doing what the new framework says it can do, changing. And here is where I have to step back and emphasize something that the script has to be honest about, because it would be irresponsible to do otherwise. I have just spent several minutes telling you that a small cluster of small earthquakes at moderate depth west of a volcano may be the signature of a leaking pipe reorganizing itself. That is a real interpretation, and it is consistent with the new research framework. But it is one interpretation. The same data is also consistent with simple background seismicity in a tectonically active region. The same data is also consistent with conventional magmatic movement that does not require any new model to explain. We are not in a position, from this signal alone, to say which reading is right. What we are in a position to say is that the signal exists, that it is the kind of signal that operational monitoring takes seriously, and that on a volcano whose framework is being rewritten right now, the small signals are worth tracking. That is the honest middle reading. Not panic, not dismissal, watching. With the new framework in one hand and the operational data in the other, and the question, what is the deep pipe doing, held open. Now let me get to the second signal, which has come from a completely different instrument, but which lands in the same picture. Part 7. The northeast crater is warming back up, and the tremor is moving northwest. The second signal that has come in from Mount Etna in the last few weeks did not come from a seismic station. It came from a satellite. A weak thermal anomaly was detected inside the northeast crater on a recent Sentinel-2 shortwave infrared image. Sentinel-2 is part of the European Space Agency's Copernicus program, and it is one of the workhorse satellites for monitoring volcanic thermal activity from orbit. The shortwave infrared bands, the SWIR bands as they are called, are sensitive to the kind of heat that comes out of volcanic features. A magma surface at temperatures above about 300 or 400 degrees Celsius is detectable in the SWIR bands even when it is not visibly glowing. Cooling lava flows, hot fumarolic vents, glowing summit craters, all of these show up in SWIR imagery as bright pixels against a darker background. Volcanologists use these images, which Sentinel-2 collects every few days for any given location, as a routine part of operational monitoring. A weak thermal anomaly in the northeast crater is, on its own, not a dramatic finding. Etna's summit craters are persistently active in some thermal sense. There is degassing going on, there are fumaroles, there is residual heat from the volcano's general restlessness. A faint SWIR signature in any one of the 4 main summit craters is not particularly unusual. What is interesting about this particular signal is the location. The northeast crater is one of the 4 main summit craters at Etna, the others being the Voragine, the Bocca Nuova, and the southeast crater complex. The southeast crater complex in particular has been by far the most active of the 4 over the last 2 decades. It is where most of the famous paroxysmal events have come from. The lava fountains that you have seen photographs of, the ones that go a kilometre or more into the air, mostly come out of the southeast crater complex. The northeast crater, by contrast, has been comparatively quiet in recent years. Not completely silent, Etna's summit is rarely silent in any deep sense, but quiet enough that a returning thermal signature there represents a change in the spatial distribution of summit activity. The northeast crater warming up, even faintly, while the southeast crater complex remains where most of the recent action has been, is the kind of small reorganization in the volcano's summit activity that operational monitoring teams flag. It is consistent with the idea that the underlying pathway is shifting. If the magma supply at depth is reorganizing, you might expect the surface expression of that supply, the active vent, the warm crater, to start shifting too. The first place where you might see that shift is in a satellite image showing a faint heat signal in a previously quiet crater. The third signal is the location of the volcanic tremor. Volcanic tremor is a continuous, low-frequency, low-amplitude seismic signal that emanates from active volcanoes. It is not made of discrete earthquake events. It is more like a continuous hum, a sustained ground vibration produced by the movement of fluids, magma, gas, hot water, through the volcanic plumbing system. Volcanologists locate tremor sources by analyzing how the signal arrives at multiple seismic stations around the volcano, in the same general way that they locate earthquakes, but adapted for a continuous signal rather than a discrete one. The result is a moving estimate of where the dominant tremor energy is being produced, a depth, a horizontal position, sometimes a rough volume. At Etna, the tremor source moves around continuously, on timescales of hours to days to weeks, as the magmatic system breathes. Tracking the position of the tremor source is one of the more sensitive monitoring tools that the Catania Observatory has. When the tremor source migrates rapidly toward the summit at shallow depths, it often precedes a paroxysmal event. When it sits in a stable position at moderate depths, the volcano is usually in a baseline state. When it begins to drift toward a part of the summit that has not been the active vent for a while, that is, again, the kind of observation that gets flagged. The recent observation is that the tremor source at Etna has been shifting toward the northwest summit area. This is, geometrically, a piece of the volcano that is close to the northeast crater, but not the same as the southeast crater complex where the recent activity has been concentrated. So you have 2 complementary signals from 2 different instruments. A sentinel, 2 thermal anomaly in the northeast crater, and a tremor source migration toward the northwest summit area. Both of them point toward the same general direction. Both of them suggest that the active part of the summit is shifting slightly, from where it has been to somewhere else. So now let us put the three signals together. A cluster of small earthquakes west of the volcano at 28 kilometers depth in the deep plumbing zone. A returning thermal signature in a summit crater that has been comparatively quiet. A tremor source migrating toward the same general area where the thermal signature is showing up. Three signals from three different instruments observing three different parts of the volcanic system, all pointing in the same direction. The deep pipe is doing something. The summit is responding. The active vent, where the magma is choosing to come out, where the heat is concentrated, where the tremor is being generated, is reorganizing. You can read this conservatively. You can say, look, none of these signals individually is large. The volcano does this kind of thing routinely. The system is talking, but it is not shouting. And the most likely outcome over the next several weeks is more of the same. Small signals, no surface change, gradual return to baseline. That reading is defensible. It is what most volcanoes in most weeks would justify. You can also read it the way the new framework would read it. You can say, the deep system is reorganizing, the pathway through the slab, and the lithosphere is shifting, the surface expression is moving northwest. And this is exactly the kind of pattern that the leaking pipe model predicts a volcano of this kind should produce when its pathway is in the middle of one of its slow reorganizations. That reading is also defensible. It is what the new model says these signals should mean. And here is the honest answer about what we do with that. We do not yet know which reading is right. The data is too sparse, too short, too small to discriminate between the two. What we know is that the signals exist, that they are consistent with each other, that they fit the framework, and that they justify continued watching. On a volcano like Etna, with 1 million people living in its shadow, with an airport that closes regularly because of its ash, with an eastern flank that is sliding into the sea, with a system whose pathway can demonstrably change. On a volcano like that, paying attention to the small signals is not paranoid. It is what the volcano demands, and paying attention is what the rest of tonight is about. Because the question now is no longer just whether the pipe is reorganizing, it is which part of the system is going to be the part that responds. The summit, the flank, the deep pipe itself, that is where we are going next. Part 8. The eastern flank is sliding into the Ionian Sea. Now we have to turn to the part of Mount Etna that does not depend on any new research, that has been understood for decades, and that is, in some ways, the most important hazard the volcano poses regardless of what the deep engine is doing. The eastern and southeastern flank of the mountain is sliding into the Ionian Sea. I want to put that sentence down and pause on it, because it is the kind of statement that, if you have not heard it before, sounds like one of those things that cannot possibly be true. A mountain that big, with a city of 1 million people sitting at its foot, with hiking trails and ski lifts and tourist viewpoints, is in motion? Toward the sea? Yes, it is. And the displacement has been measured in detail by multiple independent methods for the last several decades. The way you measure something like this from orbit is with a technique called interferometric synthetic aperture radar, or INSAR. The idea is that a radar satellite passes over the same patch of ground on multiple orbits, each time bouncing radar pulses off the surface and recording the precise phase of the returning signal. If the surface has moved between two passes, if a piece of mountainside has slid by a few centimeters relative to its position the last time the satellite was there, that motion shows up as a measurable change in the radar phase. Process the data carefully, account for atmospheric effects and orbital geometry, and you can produce a map of ground motion across an entire volcano with millimeter precision. What the INSAR record at Etna shows, and what corroborating GPS measurements from stations installed on the volcano itself confirm, is that the eastern and southeastern flank of the mountain is moving toward the Ionian Sea at rates of several centimeters per year. The number is not uniform. Different parts of the flank move at different speeds. Some segments creep at 1 or 2 centimeters per year. Other segments move faster, especially during episodes of active deformation, when a magma intrusion or a fault slip causes a temporary acceleration. The overall picture is that the eastern flank is one large, slowly displacing mass of rock and volcanic material, moving consistently eastward, year after year, decade after decade. I know that sounds slow, A few centimetres a year is not the kind of motion that anyone living on the volcano would notice in their daily life. But the slowness is misleading, because what is moving is enormous. The sliding sector covers a large fraction of the volcano's eastern flank, encompassing villages, agricultural land, infrastructure, and the basements of the southeastern flank that extend out underwater. The total volume of rock and volcanic material that is in motion is measured in cubic kilometres. When you multiply a few centimetres per year by a cubic kilometre of rock, you get a number that, in terms of energy and stress, is not small at all. It is enormous. And it is operating against a backdrop of the mountain's own weight, the tectonic forces from the deforming slab below, and the magmatic pressure from the leaking pipe within. Now here is the thing about the eastern flank that makes it different from a simple landslide hazard you might see on a normal mountain. The sliding sector does not end at the coastline. The eastern flank of Mount Etna continues offshore. The volcano is built on a sloping basement, and the part of the basement that holds the eastern flank tilts downward toward the Ionian Sea, so that when you cross the shoreline you do not actually cross the edge of the volcano. You cross the edge of the visible volcano. The hidden volcano, the part of the flank that is underwater, keeps going. It goes down to a depth of approximately 1,500 metres below sea level, that is almost 5,000 feet, below the waterline, and it is still part of the same sliding sector that you can stand on in the villages above. This has been mapped, in detail, by submarine surveys. Italian research vessels, in collaboration with the National Institute of Oceanography and Applied Geophysics, have run side-scan, sonar and multi-beam bathymetry over the offshore extension of the volcano's eastern flank for years. They have identified the geometry of the sliding sector below water, the headwall scarps, the transverse faults, the lobate scarps on the seafloor that are the surface expressions of the same kind of deformation that is happening on land. The conclusion of that work is unambiguous. The eastern flank of Mount Etna is a continuous structurally connected sliding sector that extends from the summit, across the populated subaerial slope, across the coastline, and down to 1,500 metres below the surface of the Ionian Sea. The Italian agencies have also installed seafloor monitoring instruments on the offshore part of the flank, acoustic transponders that can measure tiny changes in the distance between fixed seabed beacons, pressure sensors that can record vertical motion of the seafloor, strain meters and tilt meters integrated into ocean bottom observatories, the same kind of geodetic monitoring that on land we do with GPS and INSAR, transferred to the seabed, so that the underwater part of the sliding sector can be tracked in the same way as the visible part. This is not a routine thing to do. Most volcanoes in the world do not have continuous geodetic monitoring of their submarine flanks. Etna does, because the hazard is recognised as real enough to justify the cost. What none of this means, and I want to be very clear about this, is that the eastern flank of Mount Etna is about to collapse catastrophically tomorrow, or next year, or next decade. The eastern flank has been sliding in its slow grinding way for at least hundreds of years and probably much longer. The slide is, in some sense, the default state of the volcano. It has been doing this all along. What it does mean is that the eastern flank is a system under continuous load, with the potential, and this is the operationally important word, potential, to release that load suddenly under the right circumstances. A large dike intrusion at the right depth and orientation could destabilize a portion of the slide. An earthquake on one of the internal faults of the volcano could trigger acceleration. A change in the deep pathway, of the kind the new framework predicts is happening from time to time, could redistribute the stress in a way that pushes part of the sliding sector closer to failure. None of these things has to happen on any given day. But all of them are possibilities that the monitoring program is designed to detect early if they do happen. And here is where the central thread of the night comes back into view. Because the eastern flank, with its slow, grinding eastward motion, with its sliding sector continuous from the summit to 1,500 metres below the sea, is the most directly visible and measurable expression of the same mobility that the new research is arguing also defines the deep engine. The volcano is a mobile system. At depth, the leaking pipe pathway can reorganize. At the surface, the eastern flank is in continuous motion. The two phenomena are not separate problems. They are two faces of the same volcano. And the question of what the deep system is doing right now, which we have spent the night building up toward, is not just a question about magma supply. It is also a question about what stress is being added to or subtracted from the slowly moving flank above. Which brings us to the question of what happens on the very rare occasions when a sliding flank of a volcano actually does let go. Part 9. When volcanoes lose a flank, Stromboli, Anak Krakatau, and Ritter Island. There are 3 cases in the historical record that volcanologists return to whenever the question of flank collapse and tsunami hazard at a coastal or island volcano comes up. They are not the only cases. They are the ones that are best documented, best understood, and that span enough different scales of event to be useful as a frame of reference. We need to walk through all 3, because the question of what could happen if a part of Etna's flank were to fail suddenly is a question that has to be answered by looking at what has actually happened elsewhere. The first case is Stromboli, in the Aeolian Islands north of Sicily. On December 30th, 2002, during a particularly active phase of the volcano's eruption, a portion of the flank known as the Sierra del Fuoco, the slope of fire, the steep slope down which Stromboli sends its constant trickle of lava, failed in a relatively small but significant collapse. The collapse displaced a volume of material into the Tyrrhenian Sea, and that displacement generated a tsunami. The wave heights when the tsunami reached adjacent coasts were not huge by global tsunami standards, but they were measured in meters. Several meters of run-up on the coast of Stromboli itself, with damage to buildings and to coastal infrastructure. Smaller but still measurable wave activity reached the coasts of Sicily and Calabria. There were injuries. There was substantial property damage. There was, for the first time in decades, a real demonstration to the people of southern Italy that a flank collapse on a Mediterranean volcano can cross open water and reach inhabited coastlines fast. The Stromboli case is interesting because the volume of material involved was, in the grand scheme of volcanic flank collapses, modest. It was nothing like the wholesale collapse of a sector of a mountain. It was a piece of the volcano's most actively eruptive flank, gave way during a paroxysm, and the consequences were already significant. That tells you something about the leverage involved. Move enough rock in enough water in a short enough time, and you do not need anything close to a catastrophic event to produce a serious tsunami. The second case is Anak Krakatau, the child of Krakatoa, in the Sunda Strait between Java and Sumatra in Indonesia. On December 22, 2018, during an eruptive phase, a large portion of the volcano's southwest flank failed in a single rapid collapse. The volume involved was substantially larger than the Stromboli event. By some estimates, as much as several tenths of a cubic kilometre of material entered the sea in a matter of minutes. The resulting tsunami was deadly. Wave heights on the coasts of Java and Sumatra reached several meters. The waves arrived without an earthquake warning, because the trigger was a flank collapse rather than a tectonic earthquake, and the existing tsunami warning systems in the region were not configured to detect that kind of event in real time. The result was more than 400 deaths and thousands of injuries. The Anak Krakatau collapse is one of the deadliest tsunami events caused by a volcanic flank collapse in modern times, and it happened, in geological terms, just a few years ago. There are people alive today who lost family members in that event. Anak Krakatau is also instructive because of how surprising it was. Volcanologists knew that flank collapse was a possibility at that volcano. The geological setting was understood. The active eruption phase, which had been ongoing for weeks before the collapse, had elevated the routine monitoring. And yet the collapse itself, when it came, was not preceded by any signal that the monitoring system in place at the time was configured to recognize as the immediate precursor to a flank failure. The collapse happened in a few minutes. The wave reached the coasts in under half an hour. The casualties were a direct consequence of the gap between what the monitoring could see and what the volcano did. In the years since, the lessons from Anak Krakatau have driven changes in how we monitor at-risk volcanic flanks worldwide, including at Mount Etna. The seafloor instruments on Etna's offshore eastern flank are, in part, a direct response to the recognition that surface-only monitoring is not sufficient for this kind of hazard. You have to be able to see the underwater part of the system, in real time, because that is where the part of the failure that is most likely to be missed will be developing. The third case is Ritter Island, off the coast of what is now Papua New Guinea, on March 13, 1888. This is the case that volcanologists consider the most extreme, well-documented example of a flank collapse tsunami in the historical record. Ritter Island was a small volcanic island, mostly cone-shaped, when its western flank failed in a single massive collapse without any preceding eruption of significant size. Several cubic kilometers of material entered the water in a matter of minutes. The resulting tsunami had run up heights on adjacent islands, estimated between 15 and 50 meters, depending on the location and the local bathymetry. Damage propagation reached out to about 600 kilometers from the source. Several hundred people died, mostly on islands close to Ritter, but the wave activity was recorded far beyond. The Ritter event is the empirical anchor for the worst-case scenarios that volcanologists model when they think about flank collapse tsunamis. It is the case that says, when a volcano really does let go, what comes next can be very large. The Ritter Island case is also useful because of what it tells us about how rare such events are, and how that rarity should be interpreted. Several cubic kilometers of mountain entering the water in a few minutes is not an everyday occurrence. It does not happen at most volcanic islands on most centuries, but it does happen. The record of submarine landslide deposits around volcanic islands worldwide, mapped by side scans, sonar and seismic profiling over the last several decades, contains evidence of dozens of such events at various scales going back through the Holocene. They are not common, they are also not unique. The hazard is recognized as real. The empirical framework for modeling the resulting tsunamis is well developed. Work by Hampton, Lee and Locat in the early 2000s established the standard empirical fits relating slide volume and depth to run-up heights at adjacent coasts, and the modelling work has been applied in various studies to volcanoes that pose the largest current risks. Mount Etna is one of those volcanoes whose published modelling work has appeared in the peer-reviewed literature. The numbers in those studies are not predictions of imminent events. They are estimates of what would happen if certain scenarios were to occur, used to inform monitoring priorities and emergency planning. Now, I have to say clearly what these three cases do, and do not tell us about Etna. They do not tell us that Etna is about to fail in any one of these ways. They do not predict timing. They do not predict magnitude. They do not justify panic. What they do tell us is that flank collapse tsunamis are a real hazard at coastal and island volcanoes. The hazard is not theoretical. It is not a worst-case scenario that nobody has ever seen. It has happened, in the modern record, at 3 different volcanoes spanning a range of sizes, and each event taught us something. Stromboli taught us that even a modest collapse in the Mediterranean can produce a damaging local tsunami. Anak Krakatau taught us that a larger collapse can kill hundreds without warning. Ritter Island taught us where the upper end of this kind of event sits, in the absence of any other mitigating factors. Etna's eastern flank, with its measured slow displacement, with its sliding sector continuous from the summit down to 1,500 metres below the Ionian Sea, with its position adjacent to a densely populated coastline that includes Catania and the towns of the eastern Sicilian coast, sits in the same general category of hazard as the volcanoes in those 3 cases. Not necessarily the same magnitude, not the same timing, but the same category. And the work that the Italian monitoring agencies are doing, the INSAR, the GPS, the seafloor instruments, the constant tracking of the sliding sector both above and below water, is exactly the kind of work that, when applied to the volcanoes in those 3 cases before the events that happened there, would have made a difference in our ability to anticipate. The honest reading is this: Etna's flank is moving. Etna's flank has been moving for a long time, and will continue to move. The probability of a catastrophic collapse on any given day, given the size of the sliding sector, the rate of motion, and the constraints from the geological record is low. But it is not zero, and the monitoring is designed precisely to give us the early warning, in the event that the slow motion accelerates toward a faster motion in a way that could turn the slow grinding hazard into a sudden release. And the central thread brings this back. A volcano with a deep mobile pathway, a leaking pipe that can reorganize, is a volcano whose stress field at depth is not constant. Changes at depth can shift the load on the sliding flank above. The new framework does not make a flank collapse more likely in any direct way, but it does sharpen the question of why the monitoring matters, because the volcano's deep system, in this picture, is a system that can change, and the surface response, including the response of the eastern flank, is potentially coupled to those changes in ways the standard models did not capture. Watching the deep signals, watching the summit signals, watching the flank signals are not 3 separate tasks. They are one task, performed across 3 different parts of a single mobile mountain. Part 10, a volcano with a changing pathway, is harder to forecast. If there is a single practical implication of the new picture of what feeds Mount Etna, it is this: a volcano whose pathway can change is a volcano whose next move is harder to predict, and nowhere is that harder to predict consequence more concentrated than in the question of where Etna's next flank eruption will open. We have to spend a moment on what a flank eruption actually is, because it is different from the kind of eruption that most people picture when they think of Etna. The dominant image of Etna in the public mind is the summit fountain, the lava fountain that goes a kilometre or more into the air out of the southeast crater complex, the ash plume that closes Catania Airport, the classic paroxysm. That is what people see in the dramatic photographs. That is what tourists are hoping to see from the safety of the Etna Park trails. A flank eruption is something else. A flank eruption is when a fissure opens on the side of the volcano somewhere on the slopes instead of at the summit. Lava comes out of a vent that is not in any of the 4 main summit craters. Sometimes the fissure opens high on the flank close to the summit. Sometimes it opens lower down on the agricultural slopes. Sometimes it opens very low near the towns. The lower the vent opens, the more damaging the eruption can be, because the lava emerges with a shorter distance to travel before it reaches inhabited areas. The path it takes is determined by gravity and topography. It follows the local watersheds, the natural drainage lines, down the volcano's slopes, toward whatever is in its way. Etna's history is full of flank eruptions, and several of them have been catastrophically damaging. The 1669 eruption is the most famous of the historical ones. It opened a fissure low on the southern flank and produced lava flows that travelled all the way to the outskirts of Catania, destroying parts of the city. Reconstruction took years. Some of the lava from that eruption is still visible today, blanketing parts of the city's outer neighbourhoods, integrated into the local landscape so completely that people walk over it without noticing. The volcano has done much more in the years since. In 1992, a flank eruption sent lava toward the village of Zaffarana Etnea on the southeastern flank. Emergency engineering, controlled diversions, hastily built barriers, even an experimental attempt to bomb the upper flow channel to redirect the lava, managed to slow the advance and ultimately spare most of the village. The 2002 and 2003 eruption opened multiple flank fissures simultaneously on both the northern and the southern slopes of the volcano, and produced extensive damage to tourism infrastructure on the upper mountain. Other smaller flank events have happened in the intervening years, with varying degrees of disruption. The pattern that emerges when you look at the historical record of Etna's flank eruptions is that they happen with some regularity, and that they can open in different places at different times. The same volcano that produced a southern flank eruption in 1669 produced a southeastern flank eruption in 1992, and northern and southern flank eruptions in 2002. The vent locations are not random. They are constrained by the structure of the volcano, by the existing system of faults and fractures, by the geometry of the magma plumbing. But within those constraints, the location of the next flank eruption is not predictable in advance. The volcano will open a fissure where the magma can most easily find its way out, and the place where the magma can most easily find its way out at any given moment depends on the current state of the plumbing system. This is where the new framework matters, because if the plumbing system is reorganizing, the place where the magma can most easily find its way out is reorganizing too. The next flank eruption is more likely to open in a part of the volcano that has not been the active vent in recent years, if the pathway has shifted that way. The current signals, the deep earthquakes west of the summit, the thermal anomaly returning to the northeast crater, the tremor migrating northwest, are signals about where the system might be opening up a new route. They are not, in themselves, evidence that a flank eruption is imminent, but they are exactly the kind of pattern that, on a volcano whose pathway can change, you would look at and ask, is the system getting ready to put a vent somewhere new? And that question matters because the consequences of a flank eruption depend so strongly on the location. A high flank eruption, opening near the summit, mostly threatens tourism infrastructure and the upper trails. A medium flank eruption, opening on the agricultural slopes, threatens vineyards and orchards and small villages but rarely reaches large populated areas. A low flank eruption, opening near the populated foothills, threatens roads, towns, the Catania metropolitan area itself. The same volume of magma coming out at different elevations on the slope produces wildly different damage. So the question of where, not just whether, is the question that the monitoring is really trying to answer. This is why a volcano with a changing pathway is harder to forecast. Not because the volcano is more dangerous in some absolute sense, but because the standard tools for anticipating the location of the next flank vent, tools that depend on identifying a stable structural pattern, identifying the historically active part of the system, projecting forward from recent activity, work less well on a system whose recent activity is itself in the middle of shifting. The forecast skill, in the traditional sense, is degraded when the system is reorganizing. What replaces the traditional forecast is closer monitoring, more instruments, more attention to the small signals, a willingness to track multiple parts of the system simultaneously without committing prematurely to a single prediction. The Italian National Institute of Geophysics and Volcanology has been moving in this direction for years, recognizing that Etna is the kind of volcano that requires this approach. The new research framework reinforces what the operational practice has been quietly recognizing. The volcano is too complicated, too mobile, too unusual to be forecast by simple models. You watch it, you watch all of it, and you stay ready. The central thread continues to hold here. The leaking pipe model does not just tell us why Etna is unusual in some abstract geological sense. It tells us concretely why the volcano is hard to forecast. The pathway is mobile, the pathway is reorganizing, the next flank vent is going to open where the pathway leads, and the pathway right now may be leading somewhere it has not led in a while. Part 11. What this mountain has already done. Before we walk into the final part of the night, before we get to the readings of what the current situation actually means, I want to take a beat and give Etna its weight. Because everything we have been talking about, the leaking pipe, the slab tear, the small signals, the sliding flank, the possibility of a flank eruption in a new place, is happening on a mountain that has already done quite a lot to the people who live around it. The history is the context in which the current signals matter. So I want to spend a few minutes with the history. I've already mentioned the 1669 eruption, which destroyed parts of Catania. That event is the most famous one. It happened over the course of several months, opened a major flank vent on the southern slopes of the volcano, and sent lava flows travelling many kilometres downslope until they reached the outskirts of Catania and the coast. The city of Catania at the time was much smaller than it is today, but it was already a major urban centre, with churches and public buildings and a significant population. The lava destroyed many of those structures. Hundreds of homes were lost. The flow reached the sea, where the meeting of molten rock and cold seawater produced clouds of steam that the inhabitants of the time interpreted in religious and supernatural terms. The Cathedral of Catania, miraculously, was largely spared, with the lava splitting around it and continuing past, a circumstance that has been described in religious and folkloric language for centuries, but that geologically reflects the specific topographic and rheological conditions of that particular flow. The 1992 eruption I have also already mentioned, but it is worth saying more about. The flank vent that opened that year sent lava toward Zaffarana Etnea, a town of several thousand people on the southeastern slope. The eruption lasted for weeks. Authorities and engineers improvised a response on the fly. Barriers were built across the path of the flow, intended to slow it down. When that proved insufficient, attempts were made to divert the lava away from the town through controlled engineering interventions, including the use of explosives in the upper part of the flow channel to redirect the magma into less threatening drainages. The interventions had mixed success. Some of them worked, others did not, but the town was ultimately spared from the worst of the flow. The 1992 response is studied today as a case in volcanic hazard mitigation, both for the lessons of what worked and for the limits of what is possible against a sustained eruption. The 2002 and 2003 eruption was different in character. It opened multiple flank fissures simultaneously on both the northern and the southern flanks of the volcano. The northern flank flows damaged tourist infrastructure in the upper mountain, including the cable car system that took visitors to the high slopes. The southern flank flows reached the agricultural slopes but did not threaten major towns. The combination of multi-vent activity and the simultaneous occurrence of major paroxysmal events at the summit made this one of the more spectacular eruption sequences in Etna's modern era. It demonstrated again that the volcano can open multiple vents simultaneously in different parts of the system, and that the location of vent activity can shift dramatically over the course of a single eruptive period. Between these named events, there have been many smaller ones. Paroxysmal episodes at the summit have been occurring with frequency over the last 2 decades. Lava fountains at the southeast crater complex have become almost routine. Ash from these events has periodically closed Catania Fontanarossa Airport, sometimes for hours, sometimes for days. The disruption to air travel in the central Mediterranean is a recurring feature of life around Etna, well known to anyone who flies through southern Italy regularly. Toulouse VAC, the Volcanic Ash Advisory Centre for Europe, issues advisories for Etna ash on a recurring basis, and aviation routes are adjusted accordingly. It is also worth pausing on what life around the volcano actually looks like, because the abstract hazard maps and the published statistics can flatten that reality in a way that does the population a disservice. The towns on Etna's flanks, Zafferana Etnea, Nicolosi, Linguaglossa, Bronte, Randazzo, and dozens of smaller villages, are not temporary settlements waiting for an eruption. They are old. Some of them have been there for centuries. They have been rebuilt after eruptions, sometimes more than once, and the people who live in them have a relationship with the mountain that combines deep local knowledge with a kind of practical respect that does not show up in tourist photographs. The agricultural land on Etna's flanks is some of the most productive in Sicily, because volcanic soils, weathered from the kind of mineral-rich basalt the volcano produces, are extraordinarily fertile. Etna's wine industry is famous. Etna's pistachios, grown on the western slopes, command premium prices in international markets. The economic value of the land around the volcano is, at the regional scale, substantial. The hazard the volcano poses is real, but it is one feature of a landscape that is, in most years, generous. This is part of why the monitoring is taken so seriously. It is not just about the airport closing periodically. It is about the towns. It is about the villages. It is about the orchards and the vineyards and the working life of an entire region of eastern Sicily. The cost of a flank eruption that opens in the wrong place, that sends lava through the wrong drainage, can be very high in human and economic terms. The cost of a flank collapse that generates a tsunami can be higher. The investment in the monitoring program is, against those potential costs, a sensible insurance policy. It is also a recognition that the mountain is not, despite the centuries of familiarity, fully understood. The new research is the latest chapter in that ongoing process of trying to understand it more clearly. The Smithsonian Institution's Global Volcanism Program catalogues Etna's eruptions in detail going back to historical times. The record they have assembled documents more than 200 separate eruptive episodes since approximately the year 1500, with confidence varying by era and good documentation only really beginning around the early modern period. Before that, the geological record, preserved lava flows, tephra layers, the chemistry of the deposits, extends the eruption history back through hundreds of thousands of years into a time before any written record could capture what was happening. The central thread brings this section back as well. Each of the major flank eruptions in Etna's history happened because the volcano's plumbing system, at that particular moment, was configured in a way that let magma find its way to a particular surface vent. The 1669 eruption opened where it did because that was where the pathway led at that moment. The 1992 eruption opened where it did for the same reason. The 2002 and 2003 eruption opened multiple vents because the pathway was, at that moment, configured to allow multiple simultaneous routes. And in every case, the pathway that produced those eruptions was a transient configuration of the system. Not the same pathway that produced the previous flank eruption. Not the same pathway that will produce the next one. The volcano has been reorganizing all along. The new research has finally given us a framework for why, and the current signals are inviting us to watch the reorganization in real time. Part 12. 3 readings, and the honest middle one. We have walked a long way to get here. We started with a research paper that says Mount Etna may not be a normal volcano. We work through what a normal volcano is. We work through what the leaking pipe model says is different about Etna. We looked at the lava chemistry. We looked at the tectonic setting. We looked at the 3 current signals, the deep earthquakes, the thermal anomaly, the migrating tremor. We looked at the sliding flank. We looked at the historical record of flank eruptions and what flank collapses have done at other coastal volcanoes. Now, we have to ask ourselves what all of it actually means right now. And to do that honestly, we have to look at 3 different readings of the same evidence and decide which one is the most defensible. Reading number 1 is the conservative reading. The reading that says, look, this is Etna. Etna does this kind of thing routinely. Etna has produced small, deep earthquakes, small thermal fluctuations, and small tremor migrations every few months for as long as anyone has been keeping track. The new research is interesting. but it does not change the operational picture in the short term. The most likely outcome over the coming weeks is more of the same. Small signals, occasional paroxysms at the southeast crater complex, the eastern flank continuing its slow eastward creep, and no dramatic change in surface activity. The volcano will keep doing what it has been doing. The signals will fade or transition into a paroxysmal episode at the summit, which is a routine kind of event for Etna, and the bigger picture will look very much like it has looked for the last several years. That reading is defensible. It is what most volcanoes in most weeks would justify. Etna has produced patterns of small signals like the current one many times in its recent monitored history, and most of those patterns resolved into either continued background activity or routine paroxysmal events at the summit. The base rate of small signal clusters at Etna producing surprising surface changes is not high. The conservative reading recognizes this base rate honestly and refuses to overinterpret. Reading number 2 is the reorganization reading. The reading that says the combination of signals, deep earthquakes in a place where they have not been concentrated recently, a thermal signature returning to a previously quieter crater, tremor migrating toward the same general part of the summit, is consistent with the kind of slow plumbing reorganization that the new research framework predicts. This does not mean an eruption is imminent. It means the system is doing something different from its recent baseline, and what comes next is harder to forecast because the pathway itself is shifting. The volcano may produce its next paroxysm at the northeast crater rather than the southeast crater complex. It may produce a small flank fissure in an unusual location. It may simply continue to redistribute its activity across different parts of the summit for a while, without producing any single notable event, until the pathway settles into a new stable configuration. That reading is also defensible. It is the reading that follows directly from taking the new research framework seriously. It does not require any extraordinary assumptions. It only requires that you let the framework predict, in its own language, what kind of pattern a reorganizing volcano should produce, and then notice that the current pattern matches. Reading number 3 is the pre-event reading. The reading that says, in the long history of Etna eruptions, paroxysms and flank fissure openings have been preceded by combinations of small signals that look statistically similar to the current pattern. The base rate of such patterns, producing an actual eruptive event in the following weeks, is not high, but it is also not zero. The careful, defensible position is to watch the current pattern very closely, in case it is the early phase of a sequence that will culminate in something larger, a major paroxysm, a flank fissure opening, an acceleration of the eastern flank slide that might or might not progress further. The volcano is not signaling an imminent collapse or a catastrophic event, but it is signaling something, and the signal is the kind of thing that, in the past, has occasionally turned into something more. That reading is the most operationally cautious. It does not say the volcano is about to do something dramatic. It says, on a volcano like this, with a history like this, the cost of watching closely is low, and the cost of not watching is potentially high. All 3 readings are defensible. None of them is provably correct. The honest answer is the middle one. Reading 2. The system is reorganizing. The new framework predicts this. The current signals are the visible expression of that reorganization. What comes next is harder to forecast because the pathway is in motion, and the practical response is closer monitoring, more attention to the small signals, a willingness to watch multiple parts of the system at once. I want to take one more beat here, because this is the part where the script has to be honest about its own limits. I am not a volcanologist. I am someone who reads the literature carefully and tries to translate it for a general audience. The Italian National Institute of Geophysics and Volcanology, with its observatory in Catania, is the authority on this volcano. They have not raised the alert level. They have not issued any warnings about imminent activity. The operational position right now is, the signals exist, they are worth watching, and the volcano is in a state that justifies attention but not alarm. I am repeating that position, in this script, because it is the position the actual experts are taking. If anything changes, if INGV does raise the alert level, if there is a sudden acceleration of any of the signals, that information will be public and immediate, and you should listen to them, not to me. What I can do is contextualize what the signals mean against the broader picture of what kind of volcano Etna actually is. And the broader picture, the picture that the new research is helping us see, is of a volcano with a mobile, reconfigurable plumbing system, an unusual tectonic setting, a lava record that documents pathway changes over geological time, an eastern flank that is sliding into the sea, and a history of flank eruptions that have repeatedly threatened the people living around it. On a volcano like that, the small signals matter. Not because they predict any specific outcome, but because, on this volcano in particular, they are the language the system uses to tell you it is doing something. I also want to address briefly the question of solar activity, because it tends to come up around any major volcanic story, and it is worth handling honestly rather than letting it sit unanswered. The statistical literature on whether solar activity influences seismic and volcanic processes is real, ongoing, and not as conclusive as either the skeptical or the credulous side of the debate sometimes claims. The Marchitelli paper from 2020, published in Scientific Reports, reported a weak statistical correlation between certain solar parameters and the largest seismic events in their catalogue. The follow-up work, including the Mizuno, Kao, and Umeno analysis from 2026, did not find support for the proposed capacitive coupling mechanism under quiet geomagnetic conditions, and the broader consensus in the geophysics community is that any solar influence, if it exists at all, is small enough that it cannot serve as a primary driver of large geological events. The current solar background, as of late May 2026, is quiet by historical standards. The geomagnetic activity is low, with the KP index peaking at sub-storm levels. There is in short no plausible mechanism by which current solar conditions would be driving the small signals at Mount Etna. The signals are internal to the volcano. The reason the volcano is doing what it is doing is the reason we have been talking about all night. The leaking pipe, the slab structure, the partial melt zone, the reconfiguring pathway. The sun is not on the suspect list. And here, before we get to the last part of the night, I want to take a moment for one other thing. There are channels online, some of them with very large audiences, that take coverage like this and turn it into pure sensationalism. Artificial voices reading slightly modified versions of careful reporting. Thumbnails that lie about what the videos contain. Predictions of imminent disaster that the underlying data does not support. The information environment around dramatic geological stories like Etna is, frankly, contaminated. The defense, if you want to know what is actually happening at any major volcano, is to consume coverage from sources where you can see who is doing the work. Sources with a face, with live appearances, with citation of primary data. If a video on Etna sounds artificial, if the predictions are bigger than the data justifies, if the channel has no traceable presence behind it, treat it with skepticism. The real story, the one I have been trying to tell tonight, is interesting enough on its own. It does not need the sensationalism. Part 13. Which part of Etna is changing right now? We come, at last, to the question that the whole night has been building toward. Which part of Mount Etna is changing right now? It is the wrong question to ask whether Etna will erupt. Etna will, in the operational sense, do something interesting in the next month, because that is the kind of volcano it is. The question that matters more is which part of the system the next interesting thing will come from. Is the deep pipe, the leaking pathway through the slab and the lithosphere, in the middle of one of its reorganizations? Is the summit, where the migration of the tremor source toward the northwest and the thermal anomaly in the northeast crater suggest a shift in the active vent, about to reopen a part of the summit that has been quiet? Is the western flank, where the small, deep earthquakes have been clustering, the place where the next surface response will appear? Is the eastern flank, with its continuous slow slide into the Ionian Sea, the part of the system that gets the next pulse of stress added or subtracted? Is the offshore extension, 1,500 meters below sea level, where the seafloor instruments are quietly monitoring the underwater part of the same sliding sector, the place where the next operational signal will come from? The honest answer is, we do not know. The honest answer is that the volcano is a system, and systems do not always concentrate their responses in a single predictable place. The deep pipe, the summit, the western and the eastern flanks, the offshore extension, all of them are connected to each other through the same underlying engine. Changes in one part can produce responses in another. A reorganization of the deep pathway can shift the location of summit activity. A shift in summit activity can change the loading on the eastern flank. A change in the loading on the eastern flank can in turn affect the deep stress field. The volcano is not a set of independent components. It is one system with multiple faces. What we can say is what the monitoring is paying attention to. The Catania Observatory is tracking the seismic activity continuously, with its network of stations on and around the volcano. They are tracking the deformation continuously, with INSAR and GPS and tilt meters. They are tracking the gas emissions continuously, because the chemistry of the gases coming out of the summit fumaroles changes when the deep system changes. They are tracking the thermal activity continuously, both from the ground and from satellites, with the kind of Sentinel-2 imagery we have already talked about. And they are tracking the offshore part of the flank continuously, through the seafloor observatories that have been installed for exactly this purpose. What we as outside observers can do is pay attention to what the monitoring agencies report. INGV publishes bulletins on a regular basis. The information is open, the data is public, the interpretations are evolving as the situation evolves. If anything changes, if the alert level rises, if the signals accelerate, if a new pattern emerges that is not consistent with the routine background, you will know. There is one specific aspect of the monitoring at Mount Etna that I want to put a few more sentences on, because it does not get talked about much in the public coverage, and yet it is one of the most operationally important pieces of the puzzle, that is the gas chemistry monitoring. At Mount Etna, as at any active volcano, the gases that come out of the summit, fumaroles and craters, are continuously sampled. The instruments measure sulfur dioxide, carbon dioxide, hydrogen sulfide, helium isotopes, and a range of other species, and they do this on a near continuous basis with a combination of ground-based spectrometers and satellite measurements. The reason this matters is that the chemistry of the gases is one of the most direct signals you can get from the deep system. When the magma at depth begins to degar more vigorously, the proportion of certain species in the surface gases shifts. When the deep magma pathway changes, the ratio of gases coming out of the volcano changes in characteristic ways. So the gas chemistry is, in a real sense, a window into the deep system that operates on a faster timescale than the other monitoring tools. It picks up changes before the surface deformation has time to respond. It picks up changes before the visible thermal expression has time to develop. And on a volcano like Etna, where the pathway is mobile and the deep signals matter, the gas chemistry is one of the most reliable early indicators of system reorganization. I bring this up because it is one of the things, in the current situation, that the operational community is paying particularly close attention to. If the leaking pipe model is right, and if the system is currently reorganizing in the way that the three signals we have already discussed suggest, then we should expect to see corresponding changes in the gas chemistry over the coming weeks. We may or may not see them. Gas monitoring is sensitive, but it is also noisy, and the signatures of pathway change are not always unambiguous. But the people doing the work in Catania are watching for it, and the data, when it comes in, will be public. And here is the larger frame, the one that the new research has brought into focus. Mount Etna may not be a normal volcano. The category that volcanology has been trying to fit it into for most of the last century may not be the right category. The volcano may belong to a class of its own, fed by a deep, partially molten layer of the mantle, leaking upward through folded and partially stuck slab structure on its own changing pathways. If that is the case, then everything else about the volcano, the unusual lava chemistry, the long history of pathway changes, the sliding eastern flank, the resistance to standard forecasting models, the current pattern of small signals reorganizing across the summit, falls into place as the consistent behavior of a single kind of system, a mobile system, a reconfigurable system, a system whose next move can come from a direction the standard models did not predict. This does not make Mount Etna more dangerous in any absolute sense. The volcano was always going to do what it does. People have been living around it for thousands of years, adapting to it, and they will continue to do so. The monitoring is good, the science is improving. The new framework, if it holds, gives the science a better tool for understanding what it is looking at. That is, in a real sense, good news. But the new framework also asks us to take the small signals seriously in a way that the old framework did not. A magnitude 2 earthquake at 28 kilometers depth, in a place where small earthquakes have not been concentrated recently. A faint thermal pixel on a satellite image of a previously quieter crater. A drift of the tremor source by a few hundred meters across the summit area. Under the old framework, those signals were noise on a stable system, and the appropriate response was to log them and move on. Under the new framework, those signals are the language a reorganizing system uses to tell you it is reorganizing, and the appropriate response is to listen. And while we are on the question of debunking, I want to dispatch the other one that tends to surface around any major volcano story, which is the energy budget question. The claim that some technological system, typically the high-frequency active auroral research program in Alaska, sometimes other facilities, could be triggering volcanic or seismic activity, is one that surfaces with surprising regularity in the comment sections of any video like this. The arithmetic is straightforward and decisive. HAARP operates at peak transmitter power on the order of 3.5 megawatts. The energy budget of even a moderate volcanic eruption is on the order of 10 to the 17th power of joules, sometimes 10 to the 19th. The gap between any conceivable energy input from a technological transmitter and the energy required to drive a volcanic eruption is somewhere between 9 and 15 orders of magnitude. That is not a small gap. That is the gap between a flashlight and a continental thunderstorm. There is no mechanism, energetically, by which a system in that power range could trigger a system at the energy scale of a volcano. The claim fails the simplest physical check you can run on it. I bring this up only because it tends to come up, and because I would rather give the actual answer once than have it festering in the background of every conversation about a system this complex. I do not know what comes next. Nobody does. The careful defensible position is that the volcano is in a phase that warrants attention without alarm, that the monitoring agencies are doing their work, that the data is open and the bulletins will keep coming, and that the most useful thing any of us can do watching from outside is to stay informed by the actual experts rather than by the noise around them. What I will say is this: tonight, on the eastern coast of Sicily, there is a mountain that has been studied for 2,500 years, and that is still capable of surprising the people who study it. A research framework that emerged only in the last few years is reframing what kind of volcano it is. The signals are doing the thing the new framework predicts they should do. And somewhere, perhaps tonight, perhaps next week, perhaps next month, perhaps not for years, a part of that mountain is going to respond to the reorganization. We do not know which part, we do not know how, we do not know when, but we are watching. And on a system like this one, a leaking pipe from deep inside the earth, with 1 million people living in its shadow, watching is exactly what the volcano demands. Stay safe out there. Part 14. One last thing. The cost of watching and why it is worth it. I want to close the night with one extra beat that does not quite fit in any of the parts we have already done, but that the whole subject deserves. The cost of watching a volcano like Mount Etna closely, with the kind of monitoring program the Italian agencies have built, is real. The cost of putting seafloor instruments 1,500 meters down on the underwater part of the eastern flank is real. The cost of maintaining a continuous network of seismic stations, gas spectrometers, satellite imagery analysts, geodetic networks, and a permanent operational observatory in Catania is real. It is paid by Italian taxpayers, by the European Union science programs that partly support the work, and indirectly by the residents of the Catania metropolitan area, in the form of public investment that could in principle go to other things. Why is the cost worth it? It is worth it because Mount Etna is a volcano with 1 million people living in its shadow, with a major airport on its southern foothills, with shipping lanes on the Ionian Sea passing within range of any potential flank collapse tsunami, with agricultural and economic value extending across the eastern third of Sicily, and with a behaviour pattern that the new research suggests is more complex and more mobile than the standard models capture. The cost of being surprised by such a volcano is, by any reasonable accounting, much larger than the cost of being prepared. A flank fissure opening unexpectedly above Catania, with no early warning from the monitoring system, would kill people. A flank collapse generating a tsunami in the Ionian Sea, with no early warning from the seafloor instruments, would kill more people. The monitoring program is, in the most concrete sense, an insurance policy. The premium is paid continuously. The payout, when it happens, comes in the form of the difference between an evacuation that took place and an evacuation that did not. This is also, by the way, why open data matters so much in this field. Italian National Institute of Geophysics and Volcanology publishes its bulletins, its data, its alert level changes on a continuous and public basis. The information is not behind a paywall. The information is not the property of a single private entity. The information is available to anyone, anywhere, who wants to look at it. That openness is part of what makes the monitoring system work. Decisions about evacuations, about flight diversions, about closures of public infrastructure depend on multiple parties being able to see the same data in the same form at the same time. The transparency is the operational backbone of the response, not an optional ethical commitment. And the openness is also what makes the contamination of the broader information environment so frustrating. We have, in modern times, an extraordinary scientific infrastructure for monitoring volcanoes like Mount Etna. We have seismic networks. We have geodetic networks. We have satellite imagery available on a few-day refresh cycle. We have public bulletins. We have peer-reviewed papers being published regularly. And in parallel with all of that, we have an ecosystem of sensationalist content that takes the careful work and turns it into clickbait, often with no traceable source, often with artificial voices, often with predictions that the underlying data does not support. The result is that the public's understanding of what is happening at a volcano can be wildly out of step with what the actual data is saying. That gap, when something does happen, makes the operational response harder. It produces panic in some quarters and complacency in others. It is, in a concrete sense, a public hazard. There is no policy fix for this. The fix, if there is one, is in the choices that individual viewers make about where to get their information. Choose sources where you can see who is doing the work. Choose sources that cite primary data, INGV bulletins, USGS volcano updates, Smithsonian Global Volcanism Program reports. Choose sources that are willing to say what they do not know, alongside what they do. The story of Mount Etna, in all its real strangeness, in all its real complexity, in all the genuine mystery of what kind of volcano it actually is more interesting than any sensationalized version of it. It does not need exaggeration to be worth your attention. It is already, on its own terms, one of the most remarkable geological systems on the planet. So the close is this. Mount Etna is doing what it has been doing for 2,500 years of recorded observation, and probably for hundreds of thousands of years before that. It is restless. It is unusual. It is harder to forecast than most volcanoes because its pathway is mobile. The new research is starting to give us a framework for why. The small signals returning right now are consistent with that framework. The eastern flank is sliding, the monitoring is good, the Catania Observatory is paying attention. The people who live around the mountain know what they live next to. And tonight, on this channel, you and I have spent a couple of hours thinking carefully about what kind of volcano this actually is, and what it might be telling us when it talks. That is what a nightly debrief is for. Not panic, not dismissal, just the careful, patient work of listening to a system that has a lot to say and trying to hear what it actually means before deciding what to do about it. Stay watchful out there, and stay with the data. Part 15. A final note. On method and on the question. Worth asking. There is one more thing I want to leave you with before the night ends, and it has less to do with Mount Etna specifically, and more to do with the question of how we know anything about a volcano at all. Because the new research on Etna is a case study in something larger, in how science actually figures out that a system it has been studying for decades, even centuries, has been quietly belonging to a category it never knew existed. The way it tends to happen, looking back at the history of geology, is something like this. The standard models are built up over a long period of careful work. They explain most of what is observed. They become the textbook framework, the thing that every geology undergraduate learns, the thing that the working professionals use as the default explanatory tool. And then there are anomalies. A few systems that do not quite fit. A few volcanoes that produce the wrong chemistry, or sit in the wrong place, or behave on the wrong timescale, or output too much magma, or output the wrong kind of lava. The anomalies are noted. They are documented. They are puzzled over. But they do not on their own displace the standard models. The standard models work too well in too many other cases to be abandoned because of a few outliers. What displaces a standard model is usually not the accumulation of anomalies. It is the arrival of a new framework that explains the anomalies in a more natural way than the contortions the standard model required. A framework that, once you see it, makes the anomalies look obvious. A framework that turns the question from why is this volcano so weird into why did we ever think these volcanoes were supposed to look the same. That is what is happening slowly with Mount Etna right now. The standard arc volcano model was making the volcano look weird. The leaking pipe model, drawing on the partially molten low-velocity zone at the top of the mantle, the slab tear, the deformed lithospheric structure beneath Sicily, is making Etna look not weird at all. In the new framework, Etna is doing exactly what it should be doing, and the only thing that was weird was the framework that we were trying to fit it into. The anomaly was never in the volcano. It was in our model. This is why the question worth asking, in my opinion, is not whether Etna will erupt in the next week or month. That question is shaped too much by the daily news cycle, by the impulse to compress geological time into human time. The question worth asking is what kind of volcano we're actually looking at. Because that question has a real answer, the answer is changing as the research progresses, and the answer matters for everything else we want to know about the mountain. The kind of monitoring we should be doing, the kind of forecast we should be attempting, the kind of preparation the surrounding population should be making, the kind of attention the small signals deserve, the new framework if it holds up under continued scrutiny, and the work is ongoing, the literature is still building, the consensus is still consolidating, will reshape how we think about Mount Etna. It will reshape, by extension, how we think about other volcanoes in similar tectonic settings. It will reshape, in the longest term, how we think about the category boundaries of volcanic systems themselves, and whether the neat three-box taxonomy that volcanology has used for 100 years deserves a fourth box, or even more. That is the kind of question that makes a long night worth spending on a mountain in Sicily. Not the immediate question of will it erupt, the deeper question of what is the thing we are looking at when we look at this volcano, and what would it mean if we had been looking at it through the wrong frame all along. That is what I would leave you with. That, and the data. The data is always the place to come back to. The bulletins from the Italian National Institute of Geophysics and Volcanology, updated continuously. The peer-reviewed literature accessible if you go look for it. The Smithsonian Institution's Global Volcanism Program record, freely available. The satellite imagery, freely available. The information is there, the story is still being written, and the volcano tonight is still doing what it has always done, only now we may finally be starting to see what it really is. Good night from Project Nightwatch. The mountain is still there, the data is still coming in, the instruments are still on, the bulletins are still being written, the researchers in Catania are still working through their next analysis, the seafloor sensors are still humming, the satellites are still passing overhead, the world keeps turning, the slab keeps deforming, the deep partial melt keeps doing whatever it has been doing for the last several 100,000 years, and tomorrow, on this channel, we will sit down again with the latest data and try to make sense of whatever the world has done in the intervening 24 hours. Until then, take care of the people around you, pay attention to the things that matter, and do not let the noise drown out the real story, because the real story, on a system like this one, is almost always more interesting than the noise. Look at the data. Read the bulletins from the agencies that actually do the work. Be skeptical of any source that is louder than the science. The volcano will keep doing what it does, on the timescales that volcanoes care about, regardless of what anybody on a screen says about it. And the people whose job it is to watch it, in Catania and across the international network of researchers who collaborate on systems like this one, will keep doing their job, regardless of what anybody on a screen says about it either. That is the right relationship to have with a mountain like this one. Quiet attention, open data, honest framing, a willingness to sit with uncertainty without rushing to resolve it the wrong way. We will be here again tomorrow.